which is Introduction to Probability Distributions. That's our topic for today. And we're going to talk a little bit about some definitions, about some terms that we're going to use. Now, we already know what a sample space is. A sample space is that space that contains or that lists all of the outcomes in an experiment. And we know that within the sample space, we can consider different events, which are collections of outcomes, so subsets of that sample space. Now, for our outcomes, we've used descriptors to identify them. For example, we use brands, such as in the tools example, where our outcomes were either Craftsman or Black & Decker. We've maybe used condition. For our defective tools example or defective parts example, we divided everything into surface flaws, no surface flaws, defective, not defective. So it's a description. We can use other types of descriptions for outcomes, such as colors, right? However, that's not very helpful in this course, especially when we're having to apply these to solve engineering problems. I think it's helpful if we can assign numbers to our outcomes. If we assign numbers to our outcomes, there's a huge variety of tools that we can then use, mathematical tools that we can then use to analyze our sample space. So in order to do this, we do want to make some definitions. So let's first start by calling each different type of outcome a variable. For example, in the problem where we're looking at tools, the only descriptors for the tools was the brand, right? Craftsman or Black & Decker. So the brand can be a variable. However, we don't know when we pick a tool, we don't know which one it's going to be. So because we don't really know what it's going to be, right, we call it a random variable. And that's a term that we're going to be using a lot throughout this course, a random variable. Essentially, a random variable is one variable that has a number of outcomes and whose outcome is unknown. It could be one of many different outcomes. In that example, there's actually only one variable, one random variable, which is the brand. That's the only thing we're using to describe our tools. However, in the defective parts example we did in the last class, we had more than one random variable because we saw whether or not our parts had surface flaws and whether or not our parts were defective. Now here, we're actually looking at two random variables. One variable is, well, the existence of surface flaws, yes or no. The other variable is the existence of, the defectiveness of the part, right? Yes or no. So we have two variables in that example, and each variable has two outcomes, yes or no. So your experiments can have as many or as few variables as you can think of, right? And for this first part, we're going to focus on experiments with only one random variable. We can learn how to use it. But in the future, we're going to see how we can apply what we've learned for more than one random variable. So just to keep it a little bit understandable, remember, a random variable can have multiple outcomes, right? And an experiment can have multiple random variables. In fact, a random variable has to have multiple outcomes because by definition, if it didn't have multiple outcomes, if it only had one outcome, it's not random anymore. It's just something that is, okay? Now, in this class, we are going to follow the practice of assigning a number to each outcome in the sample space. Because again, if we assign numbers to everything, then we can deal with some mathematical tools that can help us analyze our experiments. Just to give you some nomenclature, we are going to express random variables with uppercase letters. My handwriting is a little bit worse than usual today. It's always bad, it's just worse today. So we're going to express our variables with uppercase letters, so something like X. Capital X can be a random variable. Capital Y can be a random variable. We've already seen other types of random variables, such as whether it has surface flaws, whether it's defective. So you can call it S, you can call it, well, not S, that's sample space, but you can call it F, you can call it D. Random variable is whatever you want, but you should try to write it with a capital letter just so that we're not confused. And then the individual outcomes in those random variables are then expressed with lowercase letters. So for example, little x, little y. In other words, if I write my random variable x, right, this table contains all of my random variables x, but each outcome in the random variable will be little x. So little x can be 1, little x can be 2. So the random variable big X contains all of these, but then little x's are individuals. So this is one of the little x's, which is 1, one of the little x's, which is 2. So we call the random variable big X. Each individual outcome, we call it little x. Same thing with y, right? We call the random variable, which contains everything, big Y. But then the individual outcomes, which only contain, well, which are only one outcome each, they are expressed with little y. You're going to get used to this, but just wanted to give you a heads up on the notation that I'm going to be using for this class. Okay. Just like sample spaces can be discrete or continuous, random variables can also be discrete or continuous. Now, we've already explained what discrete and continuous meant, but if you need a refresher, discrete is something that we can count. It can be either finite or countably infinite. The continuous sample spaces were those that had no gaps in between, which means there was no gap from one measurement to another, and therefore they cannot be counted, right? They are infinite and cannot be counted. For example, if you're looking at a continuous sample space between 1 and 2, where every single real number is a possible outcome, and I say, well, let's say I measured 1.001, what's the next outcome? Well, it cannot be 1.002 because between 1.001 and 1.002 is a set of infinite numbers, infinite real numbers. So we can't really say what comes next, what comes before, what comes next. Okay, we can only deal with ranges, such as one of the students said last time. We deal with ranges instead of individual events. So just like sample spaces, my random variables can be discrete or can be continuous. Can you give me some examples of what a discrete random variable would look like? Maybe an example. What is a discrete random variable that you can think of? Yeah, dice roll, says Christian. That's absolutely right. You know, we roll our die. Actually, yeah, we roll our die. Let's just do one to make it a little bit simpler. And our possible outcomes can be 1 through 6. So if we can call that random variable, we can call it R for roll. And then the outcomes there are 1, 2, 3, 4, 5, 6. We can count these outcomes. There are clear gaps in between each outcome. Therefore, it is a discrete random variable. And in this case, if I roll my die, I know that my random variable is big R, but the individual outcome that I get, for example, let's say I roll my die and I landed on a 3, then I say that little r is equal to 3, right? Because it's the individual outcome. Good. Another example, which is in the notes, is the number of scratches on a surface. Assuming that we don't care about the length of the scratch or the condition of the scratch, we can say that, well, the number of scratches on a surface, let's say the surface of a wooden table, that can be my random variable. There can be 3 scratches, there can be 5. I have cats, so there's a lot more, right? But that is essentially a discrete random variable because we can go from 0 all the way to infinity, but there's always gaps in between. I can't have 1.5 scratches, right? I need to have either 1 scratch, 2 scratches, 3 scratches, etc., or 0 scratches. Now, on the other hand, we have continuous random variables. And those give me, right, ranges with no gaps in between. For example, in the area of the number of scratches on a surface, I could call my continuous random variable the length of the scratch. And the length can be as small as no length. And let's say the scratches can only go as big as I don't know, a foot. But in between 0 and a foot, there's an infinite number of real numbers right, that can tell me or that can be a possible outcome for the length of a scratch. So that's an example of a continuous random variable taken from a discrete random variable. Any ideas of other continuous random variables? For example, if our experiment is rolling a die, we already know that the number that it lands on is a discrete random variable. Can you think of a continuous random variable that can come from that experiment of rolling a die? Like what things can we observe that could be continuous? The jump height of a sample of people. Good, that's good. We can have the jump height, so either the height from which you threw the die or the height at which it bounces, right? The time spent rolling, that's absolutely right. So I'm gonna write all those. And these are for rolling a die.
How many did we...
Can you say that again?
I realized it wasn't a good example, my bad.
Oh, okay. So we have the time spent rolling, the jump height, maybe even the noise measurement, decibels of the sound it makes when it hits the surface. So those are continuous random variables that come from a very simple experiment, right? Number of bounces, I would say that won't be a continuous random variable, right? Because I can't really quantify it as one bounce, 1.01 bounces, right? However, that could go here in my discrete random variable, where I can have my number of bounces, and it can go from 0 to 1 to 2 to 3 all the way to infinity, but it's countable, right? It's never going to be any number in between any of our outcomes. So yes, we have a discrete and infinite random variable, and then a discrete variable, and then we have continuous random variables.
The revolution since spun.
Nice, nice. Revolutions. Good. So I can tell that you already understand what all this means, and that's great because in this class, even though we're going to try to place our focus on discrete random variables, you'll notice that some of our probability distributions are going to be specific to continuous random variables, which means that we will need to understand that. So if you understand why these are discrete, so the number it rolls and the number of bounces, and why these are continuous, then you should be able to identify discrete and continuous random variables for most experiments. The lecture notes have a couple of additional examples we're not going over in this class, so you can look at those. And if you feel that maybe this doesn't seem to be discrete or this doesn't seem to be continuous, then let me know. We can talk about those. In the chat, a student asks, can the units of your measuring tool be the deciding factor to whether it's discrete or continuous? Yes, and actually that's what I was about to talk about. So you're good. You're right. I think we're right in sync on this material. So what Carlos is proposing is, what if your ruler that you're using to measure something, let's say jump height, can only be used to the nearest millimeter? And we know that our outcomes, our measurements, will only be in millimeters. Is that then discrete or continuous? What do you think? If you're using a ruler, the ruler can only measure to the nearest millimeter. Is your sample space, or sorry, is your random variable now discrete or continuous? So we have someone saying continuous, someone saying discrete, someone saying discrete, discrete. So physically speaking, it's still a continuous random variable, right? However, right, because we can only measure it to a certain degree, our measurements will be discrete. So in a sense, it's like we're saying it could be both, right? But our measurement, right, our measuring tool will force us to have a limited number, okay, a limited number of outcomes. Rounding really help because you can have a perfectly round number in a continuous random variable, right? You can measure, let's say you're measuring a height and you measure 1 foot exactly without needing to round. It's still a continuous random variable. So whether or not we round is not really important, but our ability to measure those outcomes is what becomes important. So I wanted to just go over some of the stuff that's going on in the chat because I think it's very, very relevant to the class, right? One student things discrete because you cannot have something in between 1 millimeter. Okay, that's good. So there's a clear gap between your measurements. Another student asks if it can be both, and we talked a little bit about that. Physically, it can be a continuous random variable, but perhaps effectively for the purpose of our experiment, we can only treat it as discrete. And then the other student actually answered that question, right? Your answer would actually be discrete. And then we have, because you can always go to the next decimal point without the ability to track that past a certain point, it makes our answer discrete. And yes, that's correct. And I like that you're all thinking about this, because that does mean that you do have a sense of understanding here. Our measuring tools are going to dictate whether we can treat this as discrete or continuous, but there's also the sense in that physically a random variable could be continuous even though our measuring tools cannot measure it as continuous. In fact, if we think of it realistically, is there any sort of measuring tool that can actually measure a continuous random variable continuously? Because all of our measuring tools are going to have a certain level of precision that they can meet, and then they cannot go further than that. So realistically speaking, we could even say, well, technically everything that we measure, right, is measured as discrete. Everything is limited, right? But we can still have physically continuous random variables. And it's important to understand these, right? Because even though we are limited in our measuring techniques, if we can recognize that a variable is continuous, even though we measure it and we have a limited measurement, so our measurements are discrete, if we recognize that it is continuous and we treat it as continuous, we are going to be able to physically interpret the variable correctly. But if we just say, hey, my ruler only measures 2 millimeters, therefore I'm going to treat this as discrete, and we try to apply it or fit the data into a discrete probability distribution, we may not get the results we are looking for. And you'll see that in most cases, our probability distributions become at best approximations when they are discrete, but they can become very, very, very precise when we treat them as continuous. So I'm glad you're all thinking about that. I'm glad that you have a good sense of what is discrete and what isn't. In this class, we are going to go the idealized route, where we say that if we're continuous random variable, we're going to treat it as continuous. So we're going to assume that we have these perfect instruments that can measure everything perfectly. But when you go out into the field, of course, you know that you are going to have limitations, but at least you'll have a good sense of understanding of how to treat variables or how to treat seemingly discrete variables as continuous and vice versa. So I'm pretty glad we're all thinking about these things, because that's going to be very, very helpful throughout the rest of this course. So we talked about random variables, and I didn't want to define that term because it is I consider, a term that we're going to be using a lot in this class. But the topic of today is not really random variables, right? It's probability distributions. So let's introduce those probability distributions. Okay, so essentially, we've already talked about equally likely outcomes, where every outcome in an experiment is equally likely to occur. And we said that when we have equally likely outcomes, then that means that the probability of each outcome is the same, right? It was going to be 1 over n. For flipping a coin, it's 1 over 2, that's 50%. For rolling a die, it's 1 over 6. But we also said that not every experiment had equally likely outcomes. Sometimes different outcomes will have different probabilities. And if we can associate those different probabilities with each individual outcome, then essentially we are creating a probability distribution. For example, we can say that we are flipping a coin or rolling a weighted die, right? Our random variable r can still have the same number of outcomes, 1, 2, 3, 4, 5, 6. But perhaps because our die is weighted in a certain way, the probability of those outcomes will actually be a little bit different. Right? The probability that our random variable is equal to any one of these individual outcomes may be different. Let's say this die is weighted so that it lands almost always on 3. Perhaps we could end up with a probability of 0.9, depending on how you roll your die, 0.9, that your die always lands on 3. And then we have 1, 2, 3, 4, 5 different probabilities. So we can probably give those 5 different other outcomes. So we can probably give them enough probability such that we reach 1. But possibly the numbers that are closest to 3 will have a higher probability. Numbers that are further to 3 will have a lower probability. But I can't really recall right now what's the face that's right behind 3. So if anybody knows that for a die, then let me know. Because I don't know what's the face that's right behind the 3. A 4? Okay. So we can give the 4 the always equals 7. Oh, thank you very much. So we can give the 4 the lowest probability, and then 1, 2, 5, and 6 a little bit higher probability because they are closest to 3, adjacent to 3. Now, I don't want to really embarrass myself by not doing the math correctly here. So what I'll do is I'll just assign 1, 2, 4, 5, and 6 equal probabilities, right? So they need to add up to 0.1, and there are 1, 2, 3, 4, 5. So how much is that? 0.02 each one? Okay. What we've just done here is create a probability distribution. That's as simple as it is. A probability distribution is a little table that pairs up each outcome with its own probability. It's a table for discrete random variables. It's a curve for continuous random variables, because random variables, if they're continuous, then you don't really have outcome 1, outcome 2, outcome 3. You actually have ranges of outcomes, and each range of outcome will have its own little probability. So for a continuous random variable, your probability distribution, and just to give a very, very idealized example, could look something like this, right? Where this range of outcomes has this probability, this range of outcomes has a little bit higher, this range of outcomes has a little bit higher. Now we need to discuss a little bit more here, because now that we're dealing with the curves, we need to deal with integrals and all that stuff. So let's not get too focused on the specifics. Right now, what matters is that the probability distribution tells me what is the probability for each outcome, or in this case, for each range of outcomes. Like from 0 to 2, we can say from 2 to 6, and then from 6 to 8, they all have different outcomes, okay? So that is our probability distribution, and that's the focus of today's class. We're going to talk about different types of probability distributions and how we can actually understand these probability distributions and analyze them using a certain set of measures. Now, the first thing we're going to start talking about when it comes to analyzing a probability distribution is its probability mass function. Or you'll see it written down as PMF for short in the textbook. So the probability mass function, or PMF for short. It's essentially a small function that describes the probability distribution of a discrete random variable. That's all it is. Now, there are several different qualifiers for a probability mass function. For starters, you already know that a probability cannot be, right, negative. Right? We know that, right? We don't have negative probability. And because the probability mass function, it's just a function that outputs the probability, then that probability mass function also cannot be negative. So my probability mass function, which is sometimes written as lowercase f of x, has to be greater than or equal to 0 for all x. And this x just means my outcome. It could be r, it could be y, it could be whatever variable I'm using. I'm just using x here. So in this case, it's kind of hard to turn this into a function. This would actually be a little bracketed function where from, for x equals 1 and 2, this is the probability mass function for 0.02. For x equals 3, it's 0.9. For x equals 4 to 6, it's 0.02. Now you may say, wait a minute, that's even harder. That's just more work. Why not just write a table? And you're right. But you'll see that when it comes to continuous distributions, it may actually be easier to write everything in terms of equations and functions. So let's keep that in mind. A probability mass function is essentially a function that outputs or spits out this table. That's all it does. Now, because your output can never be more than 1 or can never be less than 0, and also more than 1, but can never be less than 0, then you know that your probability mass function cannot be less than 0 as well. We said that a sample space always has a probability of 1, which means that a sample space always occurs. Now, if we're looking at this event or at this section of the sample space that looks at this one random variable, you'll notice that it doesn't matter if we have 1, 2, 3, maybe 5 different random variables in my sample space. The outcomes of those the probabilities of those outcomes are going to also have to add up to 1. Notice that it doesn't matter if we're measuring number of time or the roll you get, and you're also measuring jump height. Whatever thing you're measuring, the sum of these probabilities always has to add up to 1, regardless of other variables or not, because there is no other option for the die to roll on, okay? So from this, we get that if we take all of the probabilities of all of the outcomes in any random variable, and we were to add them up, so we take the sum of all of the probabilities, and let's just call this xi, all the probabilities, all of the outcomes in any random variable, and let's call this from I equals 1 to n, where n is just the number of outcomes in the random variable. What should that sum equal to for any random variable? We take all the probabilities of all the outcomes in any random variable and we add them up. Yeah, it has to equal 1, right? It has to equal 1 because that is my entire sample space. If I were to look at jump height and I look at all the probabilities and of all the outcomes of the ranges of outcomes and I add them up, that also gives me 1. Okay, so that's another function or another property of a probability mass function. Then the final property is that the probability mass function, which is f of x, essentially all it spits out is this number. And because it spits out this number, basically it's saying that this equation or function is giving me the probability that my random variable is equal to any individual outcome. Now, it's important that we understand this because sometimes you'll see it written in this way. Sometimes you'll see the probability mass function expressed in this way, but in both cases for discrete random variables, they mean the same thing. So probability mass functions can never be less than 0. They have to add up to 1, and then they're equal to the probability of the random variable being equal to any of the outcomes, any one outcome. Okay? Now, it's important to understand all this, but it's also important to be able to use it as well. So let's look at an example from the textbook, which, by the way, you may notice if you saw the notes for this week, that this week we are going to be focusing primarily on the textbook, mainly because we're going to be introducing some of the equations that we're going to have to use throughout the rest of the class. So this week, unfortunately, I did not really bring in material from other sources as I tried to do in previous classes, but mainly because there is a lot of material to cover, right? And I couldn't really supplement it because we're probably going to take up the entire class. Probably, who knows? So let's look at this example from the textbook, which is a camera flash test. One amazing property of the textbook is coming up with examples that I really don't care about. As in, I will never test camera flashes. But if it interests someone else, then I guess it works. So let's say that you perform 3 tests on a camera flash, and you use the data from your experiments to develop a probability distribution. In your probability distribution, the random variable x is going to represent the number of times the flash passed the test. In other words, you use a camera flash, and then if it passed the test, then good. If it didn't pass, then okay. So the number of times the flash passed the test is your variable x. The first question will be, is that a discrete random variable or a continuous random variable? The number of times the flash passed the test. In other words, the number of times the flash worked. Let's say worked. The number of times the flash worked. Is that discrete or continuous? Discrete? Okay, good, because it's number of times, right? There's clear gaps. And let's say that your data, right? Let's say that you ran the test 3 times, right? You performed 3 tests. And because of that, your outcomes can be 0, which means that the flash did not pass any of the tests. 1, 2, or 3. That's essentially what your data is. That's your random variable. Now, with the results, you developed the following probability distribution. In this case, I could call it probability that x equals little x, or we also know that that's the same as my probability mass function. It's the same thing. And we get the following distribution. Now, here's my question then, okay? What is the probability? Okay, well, what's the probability that if we pick one of the cameras at random, okay, just one camera at random, the camera's flash only passes 2 of those tests, okay, only passes 2 of those tests. Any ideas? You may not want to look at the notes there. Just look at the table here. So what's the probability? We pick one of the cameras at random. Its flash only passes 2 of the tests. So Samuel says 38.4%. Okay. So if we look at our data, what's this data telling us? Saying that the probability that the camera passed 0 tests, no tests, was 0.008. The probability, okay, that my flash passed 1 test was 0.096. The probability that my camera passed 2 tests is 0.384. And the probability that the camera passed 3 tests, okay, is 0.512. So Samuel, I'd say you're right? We're looking at the probability that my camera only passes 2 tests, and that's 0.384. There's an error in the notes, so I'll fix that and update the notes shortly. But yeah, that's correct. So all we're doing here, right, is putting our data together and then just looking at each outcome. That's it. So when I asked, what is the probability that the camera only passes 2 of the tests? Essentially what I'm saying is, what is the probability that my number of times the test passed is equal to 2? But we already know from this definition that that's the same as just the probability mass function of 2. And since that's already detailed in this table, then we know that that's going to be 0.384. Couple of notes. It may be helpful to add up all these values and make sure that they add up to 1, because if they don't add up to 1, right, then that means that your probability distribution is either incorrect or incomplete. So just as a general practice, especially when you're dealing with data that you didn't actually collect, okay? So that's essentially how we use a probability mass function. That's all it is. We have a probability, and then we select it based on the outcome that we are looking for, okay? Now, I have another question following up on this example. What if I want the probability that my flash passes up to 2 tests? In other words, that my camera flash passes 0, 1, or 2 tests. So I can say that, I can write this down as a probability that my random variable is less than or equal to 2. So what's the probability that my camera passes up to 2 tests? All right, it looks like everybody's saying add them up to add them up. And Renee has a shortcut, right? Just take 1 and subtract the probability for 3, all those are correct, right? And if you add them up, what do you get? 0.488, correct? Now this is actually going to be very important because we'll notice that in a lot of the different experiments that we end up trying to apply statistics to, perhaps a specific value, a specific outcome is not really what we're looking for. Perhaps we're looking for a range. Even in discrete random variables, perhaps what we're looking for is a range. So this type of probability is one that's going to show up a lot in class, and that's what we call a cumulative distribution. Where instead of actually looking at a probability for one specific event, we turn to the probability of a range of events from the first outcome all the way up to that one event. So that's what we call a cumulative distribution. Let's see if we can generate our cumulative distribution for this table. Here we're looking for the probability that x is less than or equal to x. Well, we see that a camera can pass 0 tests, but it cannot pass -1 tests, right? The camera, it either passes your test or doesn't pass any test, right? But it cannot pass negative tests, which means that 0, which is the lowest number, can only have a probability of up to 0.008 because there's nothing else before it. Now, what's the probability that a camera test passes up to 1 test? Well, we know that a camera flash can pass no test, or it can pass 1 test. So what's that probability? Okay. And we know the probability that the camera test passes up to 2 tests is 0.488. And what's the probability that my camera flash passes up to 3 tests? 1, correct. Now that should give you a clue here, right? That a cumulative distribution, that table is always going to end in 1. Because if it's cumulative, that means that the last value tells me what's the probability that all of this is satisfied. And we know that the probability of every single outcome in a random variable has to add up to 1. So the last value in a cumulative distribution is always going to be 1. Now that gives me a chance to introduce the cumulative distribution function properly. I've seen it written down as CDF. Not sure if I would use that that nomenclature that much, but essentially cumulative distribution functions, they follow these properties, right? The cumulative distribution function, first of all, we typically write it down as capital F, and that is going to be equal to the probability that my random variable is less than or equal to any of the outcomes. Of course, we know that my cumulative distribution function is going to be a number between 0 and 1. We know that much. We know that the last value of a probability distribution, when it's cumulative, it has to be equal to 1. And then we know the following, right? We know that if some value x is less than or equal to some other outcome y, then the cumulative distribution function of x also has to be less than or equal to the cumulative distribution function of y, right? Because if one number is smaller and it's cumulative, then the probability of y has to include the probability of x within it. So that's why it has to be, y can be greater than or maybe even equal to x. So that's the idea behind a cumulative distribution function. We've already been able to develop this cumulative distribution function, okay? It's actually very easy to write down these functions in Excel. In fact, I will say that for this class, it is important to know how to develop them in Excel because moving forward, right, some of the more advanced topics are going to have us deal with a lot of data, and perhaps dealing with a lot of points is made a little bit easier if you're using spreadsheet software. So if you want to take some time to practice it on your own, later after the class or during the break, you can write down this table in Excel and then use some function or some use some in-cell function or something, or some in spreadsheet function to actually develop this table. I think you can all tell that it's a pretty easy process, right? Because the algorithm is very simple. It's always going to be the value of your probability, and then you add up all the values above it. But you can see here that if this first value just adds these two up, then all this next one has to do is just add your probability plus the value above it, and that's all it is. So it's a relatively simple thing to do in Excel. I would recommend that you figure out how to do it so that in the future when we're dealing with a lot of data, then you are able to actually solve it correctly. Okay. So we talked a little bit about what probability distributions are, but of course now we get to go to the semi-fun part, which is how to analyze them. We can see them, we can identify them, but I've mentioned that there's a reason why we want to use numbers, right? There's a reason why we assign numbers to these random variables. And that reason is because these numbers will allow us to analyze and study our probability distributions through the use of mathematical tools. Using mathematical tools allows us, right, to try, or at least attempt, to have a more objective approach to how we view our data. And this doesn't mean that our end result will be completely free of biases. In fact, we'll learn later that it's, your biases actually travel with you throughout the entire life of your project, right? But at least it gives us a standard framework from which we can all agree on, right? If we all part from a framework that we all agree on, and that's the framework of using mathematical tools, then we will at least have the same data and the same qualifiers to describe that data. Okay, so what we're going to study now are the different measures that we use to study probability distribution. So what are these measures? The first one is one that you've already heard of before, but you may not be entirely sure about what it means, because it does have different meanings depending on what it is you're studying. So the very first measure for today's class is the mean. Can somebody tell me, in your very own words, what is the mean for you? What does that represent? Somebody says the average, somebody else says the average. Okay, that sounds decent. Somebody says it's not the average. Okay, so can you give us an idea of what mean is then? It's one measure of average. Okay, that sounds a little bit more professional. So it's like there's many averages. I'm not really sure if I agree with that. Maybe I do, who knows? But in your own words, if you were to describe the mean to someone, the middle number, I would say no. And we're going to deal with that later, what the middle number is. We're going to deal with that later. That's median. That's correct. Think of the mean, like physically speaking. If someone were to ask you, please describe to me what the mean is with this set of data, how can I find it? Like, or how do I express it? What does it mean? What does it tell me? The sum of all values divided by the number of values. That is, I think, what everybody else has been calling the average, or the arithmetic average. Okay, but that's not really quite the mean, right? Sorry, go ahead.
I was gonna say the value that best represents the data set, or what the data set is trying to say.
I like what you're saying. I disagree with you, and we'll explain why when we talk about descriptive statistics. I disagree with you when you say best represents, but I like that you're thinking in those terms, right? Because again, why are we trying to find these measures in the first place? Well, we're trying to analyze our data set. So if we're analyzing our data set, then the mean has to have some significance to our data as a whole. Now, it seems like we can all agree, based on all of your answers have one thing in common, right? For mean, you're looking at one value that seems to represent our data. Whether you call it the average, whether you call it the median, whether you're adding everything, dividing by a number of values, all that you're giving me, right, is a number to represent your entire data set. And I think at least in spirit, you are correct. However, mathematically, that's not really what the mean is, but at least we have the idea of what we're looking for. Jaden
Well,
gives me another idea. Oh, sorry, go ahead.
oh, I was going to say, well, does it have anything to do with the fact that the mean is used in the standard deviation of a data set?
Yes, but we haven't defined standard deviation yet, so I can't
Okay,
really
yeah,
expect you
yeah.
to use it, right?
I was
Um,
trying to find that kind of relationship there.
Yeah, no. Well, I like that you're thinking a little bit ahead. That's really good. And I like that we understand that the mean is going to be one value, and for some reason that value is going to be a representative of our data set. Good, good, good. Let me give you some quick examples just to explain to you why I don't think the mean is necessarily just the arithmetic average, okay? Or the number that evenly distributes into the total, which is actually the same as just adding everything and dividing it by n. So I'll explain why I don't think it's that. Let's look at grades. Let's say that you all took my first test, and let's fast forward to next week. Everybody took the test. I would like to have a measure for which through which I can describe the performance of your class. Now, how can I do that if there are, let's see, there are 23 students here right now. I'd like to measure your performance in class, but the 23 of you are going to have different grades, right? So how can I maybe find a number that says, hey, if I could grade the entire class as one, like this is what they would have gotten, or this is the number that represents how the class is doing. Let's say I want to compare my class to somebody else's data collection class. How could I find a number based on your test grades that gives me a representation of how you're doing as a whole? The median, that's an example, right? Pick the middle value. Okay, good. Another example I would say is just the average, right? You just take all the grades, add them up, divide by the number of students. I think those two are good measures, right, of what the class is doing like as a whole. And that's good. That's one type of mean. Those are two different types of mean that kind of represent my data set. But let's now look at your individual grades. Let's say that you are taking my class, but you're also taking a lab. Labs are typically 1 credit hours. In fact, there's one student here that's in this class and also in my lab. Suppose that you have this very, very hard report for the lab, and it's due on the same week that you have a test for my class. In fact, that's the situation that this one student is in right now. But let's say that you have these other responsibilities, so you can only dedicate time to one of the two. You can only study for my data collection test, a 3 credit hour class, or you can work on your fluids lab report, a 1 credit hour class. If you only have the choice to do one of those two, and you know that the other one you'll fail, which one do you think you would choose? And I think this is a real situation that a lot of you have found yourselves in. Okay, looks like the test is weighted more. Okay, the one with the most weight. Okay, I like that you're saying that. So what do you mean by weight? Okay, for my GPA, 3 hours is more than 1. That says Renee. Carlos says it controls the average of your grade a little bit more. Okay, I like that, Carlos. Bailey says the effect that it has on your final score. And Christian says one of them has a greater overall effect. I think you're all correct, right? It seems like one of these grades, because it's a 3 credit hour class, is going to affect your GPA more than a 1 credit hour class, right? Because they're weighted differently, okay? Now, if that's the case, and I want to calculate my student's GPA, or you, the student, want to calculate your own GPA, you can't just add up your grades for data collection and your fluids lab and then divide by 2 because you're taking 2 classes, right? You can't do that because their weights are different. And that is the importance of the mean, right? The mean in this case is not going to be represented by the average of your 2 grades. It's actually going to be represented by a value that's weighted by your 2 grades. a really good indicator of the mean of your grades is your GPA, because your GPA takes into account not just what grade you got in each class, but also how much weight does each class have towards your overall development as an engineer. We can disagree on that, but that's a different conversation. But essentially, that's what your GPA does, right? It measures your grades, but then weighs them against how many hours, right, of dedication you should dedicate to each class. And you'll notice that even though your grades are A, B, C, D, F, what the GPA does is it takes them and turns them into numbers, 4, 3, 2, 1, 0. And that's the same procedure that we've been doing in class so far. We're taking a random variable and we are turning it into a number so that we can take that number and calculate a representative value, which is what we call the mean. I think it's a good time to take a break. I really like the way this conversation is moving along. It seems like you all have a really, really good idea of what it is I'm looking for. All right. But let's take a 15-minute break and meet back at 3:30 so that we can continue to talk about these measures.